Okay, so let's go over the review for APSTAT here. So a researcher studying reaction times of drivers state that a 95% confidence interval for the mean time it takes for a driver to apply the brakes after seeing the brake lights on a vehicle in front of him is 1.2 to 1.8 seconds. So 1.2 to 1.8 seconds. So let's figure out so that's 1.8 minus 1.2. So or let's find the middle. So let's add them up. So plus 1.2. I divide by 2. So the middle would be 1.5. So I know it's one of these. That's going to be the point estimate. Then the difference between one of the ends, like 1.8 minus 1.8 minus. I know you could probably do this in your head, but it's 0.3. So that it's got to be E. So you just average them and then find the distance between the center, the point estimator, and one of the sides. Collect a random sample of n from a population, and the data collected compute a 95% confidence interval. Which of the following would produce a wider confidence interval based on the same data? Okay, I'm going to start with B here. So use a smaller confidence level. So if you think about when the alpha goes down, which probably produce a wider confidence interval. So scratch that for a second. So this one, let's just check it. So use a smaller confidence level. So if the level was, if I'm like 60% confident, what would happen there? That would produce a smaller confidence interval because like I'm less sure, so I'm taking a better guess. Like I think, oh, maybe within 1%, but there's a less chance of that happening, so it's going to do the reverse. Use the same confidence level, but compute the interval n times. Approximately 5% of those intervals would be larger. I'm just going to cross that one out. It doesn't jive with anything we've done. Increase the sample size. Okay, that actually is going to give you a smaller interval because you're going to have a better estimate. So that's always good, which is not what we want. We want a wider interval. Nothing can assure that you would get a larger interval. One can only say the probability of obtaining a larger interval is 5%. I don't think that makes any sense. And this is the opposite of B is A. So if I have confidence level of 99%, I want to make darn sure that I've got everything in the interval. So the interval is going to be pretty wide there. Okay, let's look at this data. So you can see right away that none of these sample sizes here are large enough to justify at least 30. So that's not good enough. So you want to find, the shape of this thing. So which one, this one looks skewed, maybe left. This one also skewed left, I think. This one looks approximately symmetric, so I think it would be Z. Again, the n values just weren't big enough there. Dan is planning to construct a confidence interval for the mean price of 3-year-old Honda Civics. He initially plans to take a simple random sample of 25 cars from a used car website, but a statistically informed friend suggests that he sample 30 cars instead. Which of the following describes what Dan's friend is most likely thinking about? Okay, so he wants to sample at least 30. So it's too small. So, good question. Okay, so it's too small for constructing a meaningful. It might be. I don't know what the shape would be, but it might be meaningful. I'm not sure that's the right answer. If n is smaller than 30, the standard error of the mean cannot be. I don't think that's true. And the sample mean of unbiased estimator. I don't know. So these two are the tempting answers, I think, because he knew n is greater than 30, and it's dealing with the central limit theorem. Is not an unbiased estimator or is an unbiased estimator. So I think it's going to be D. Let's see. So it ensures the sample distribution is approximately normal, even if the population is skewed. That's true. Should simply is an unbiased estimate. See, that's not really the central limit theorem. It's all about the shape and the variation goes down, but that's not really, unbiased estimator is not part of the central limit theorem. The government claims that students earn a mean of 4,500 during their summer break. Random sample of students gave a sample average of 3,975, and a 95% confidence interval was found to be between those two numbers, which if following is a correct interpretation of that. Okay, so I like that, if we took many samples, it doesn't sound too bad. True that there's 90% probability. I don't think that sounds right. That's not how we talk about it. Does not gain the value. There's a 95% probability. I don't think that's it. For your repeater samples, 95% of all contain that. So E doesn't look right. That's, we got that interval this time, but we get a different one next time. These two are very close. There's not a ton of difference between them. I don't really see a problem with C. I like D better, but they're pretty darn similar. I'm not sure if an AP question would put something those close together there. C is very close to being right there. Bags of a certain brand of tortilla chip claim to have a net weight of 14 ounces. Representative from the Consumer Advocate Group wishes to see if there's any evidence that the mean net weight is less than advertised and plans to make a 95% confidence interval. Using a simple random sample of 16 bags, suppose he is not sure if the distribution of net weight is normal. In which of the following circumstances might he not be safe to use a T procedure? Okay, so what are the conditions here for this? So which one would not be safe? Ooh, this could be interesting here. So the mean and median of the data are nearly equal. That probably means it might be kind of a normal type of data. That's usually true. So that doesn't sound unsafe to me. Histogram of the data with a single peak and is roughly symmetric. That sounds somewhat normal, so I don't think that scares me. A stem plot that has a large outlier. A large outlier is very scary to me. I think that's going to be the answer. Sample standard deviation is large. Might be teensy bit dangerous, but I don't know about that one. And then none of these circumstances, so I think it's got to be C. We don't want to see large outliers for that. Which of the following confidence intervals has the largest critical value? Okay, so 95, so I know that's 1.96 right there because I have it memorized for Z because it's easy to memorize that one. It's the most popular one. If we use this one, so let's try this, a menu 6.5. Oh wait, well we got it. So for T critical value, you gotta draw it 95%. There's gonna be 2.5 right there. So if you go inverse T, oops. Okay, so distributions inverse T. So if we go 0.975, degrees of freedom would be 1. Wow. Okay, so then we change that to 0.975. Okay, I think that's the same with degree of 10. That's 2.2. Which one has the largest? Okay, so so far that one does. This is the next one would be if you draw like a 95 or 90 here. So there's 5 to the left of that. So 95 would be your inverse T there. So, and it was with 1 degree of freedom. 10. So the biggest is B, 12. That's pretty big. A researcher wants to see if birds that build larger nests lay larger eggs. She selects two random sample nests, one small nest and the other large nest. She weighs one egg from each nest. The data is summarized below. Which of the following represents a 95% confidence interval for the true difference between the average mass of eggs and this large test? Okay, so this is a two-prop interval. So the formula, these are means, right? So we might have to think about that formula we need for this one. For the two sample t interval, it's going to be the x bar 1 minus x bar 2 plus or minus t critical value times square root of, it's like standard deviation of the 1 squared over n1 plus standard deviation of the 2 squared all over n2. So something like that form. So right away we see these numbers aren't squared. This is just all wrong. This is all wrong. So it's got to be one of these guys. So let's see what the differences are. So they're divided by 60 and 159. So I don't know where those are coming from because that's just n, not degrees of freedom there. So it's got to be A. Student APSTAT project involves comparing the time it takes a student to complete a set of 25 basic trinomial factoring problems while listening to either rap music or country music. 12 students are timed on different sets of problems, and the order in which their sets appear are randomized. Resulting data is thus paired, with each student acting as his own pair. Which of the following conditions is required to construct a 99% confidence interval for their paired data? Okay, so conditions. So we're looking for conditions for paired data. Well, that's the same as one sample thing. So we need a random sample. We need less than 10%, large sample. Okay, so let's see what this one would be. Okay, so the distribution of times for all students on each set of problems must be approximately normal. Which of the following conditions is required? So is that a condition? So I don't think that's actually a condition. Times for all students must be approximately normal. Again, not a condition. We're using a t-curve here, I think, right, for means. The distribution of times for all 24 sets of problems, 12 students are taking two sets, must be approximately normal. Each t-test. Okay, so this is paired, right? Let's just talk about what this is. So this is paired. So we want to, it's a tough one. So I did think of all students, so it must be approximately normal. I don't think we need that. We need the differences to be normal. The differences, that's what we're looking for. Remember, paired data is all about the differences. And so that's why D is correct. The other ones are close to correct. It's hard to, knock them all out there, but paired data, it's all about the diff. So you're taking the two values and subtracting them to get the differences. Two independent random samples of size n equals 50 and 75 are drawn from population 1 and 2. In order for T procedures to be valid, what must be the size of the population? So we have to sample less than 10%. Right, so N1 could be at most 500, N2 could be most 750. So I think that would be B. This is not that bad, if you know that property. Okay. For years, Alex has kept careful records of the time it takes to commute from his home to a place of work. On average, it takes Alex 28.4 minutes to travel from home to work. Department of Transportation installed 2 additional traffic lights along the roadway. And he's concerned these new lights may take him more time. He records home to work travel time for a random sample of 12 days. Mean travel time for those 12 days is 30.2 with a standard deviation of 2.4. Expected data shows no skewness or serious departures from normality. Construct a 95% confidence interval for the mean home to work travel time in the model route. Okay. So let's start with what is mu? So this is the Alex's true mean home to work commute time along the route. The confidence level you need to put on there some, I just write that one. Confidence level is 0.95. So when you plan, you say, what type of test is this? This is a one sample T interval for means. Is this random? So just say something about random sample. So I'm gonna write that and say the words random sample. Check. Okay. 12 is less than 10% of the population of all possible home to work commute times. The sample size is small, and it says it shows no skewness or serious departures from normality. So large sample condition. I guess we just reference that. We don't have a graph to draw on there. So write down, what things are. So, the standard deviation is to tell us 2.4, and it's 12. I would consider doing this one in your test at this point in your calculator. So you go to menu, 6 intervals, so 6, and this is a T interval. We're going to use stats here. So X bar is 30.2. Standard deviation is 2.4. N is 12. And it's 95%. Okay. Okay, so degrees of freedom is 11. Somewhere on here, definitely write, degrees of freedom is 11. So I like to plug into the formula, so I'd show the work 30.2, especially as you're kind of learning this. To get that T critical value, you might have to kind of draw it and go, okay, 95. So there's 2.5 to the left. So use your inverse T command, 0.975, comma the degrees of freedom, which is 11. And that should give you, I think the T value ends up being 2.2 on this one, times 2.4, which is standard deviation, divided by square root of 12. And then you could, again, use your calculator at this point to say 30.2 plus or minus margin of error, which is 1.52. The lower bound is 28.6. The upper bound is 31.7. Okay, so we are 95% confident. The interval from 28.6 to 31.72 captures the true mean of home to work commute time along the modified route. So the follow-up question is, using the confidence interval, do you agree with Alex's concern, right? So should we be concerned? So the old interval is 28.4. Oh, 28.4 is not in the interval. 28.4 is not in the interval, right? So, which is evidence that new traffic lights have changed the true mean. It seems to take longer. So I would say something like that. So 12, this looks like a classic 2-sample T interval here. It's not paired data, so we're looking at just the overall. We're not comparing individual students here. You can kind of tell we don't know any of the individual students. We don't have a list of differences. There's no way for us to do this if it's not paired data. So they just sampled 41 girls and 41 boys. They didn't pair them up by some reasonable quality like height or something, and do that. So I just measured every child. This is the differences. What additional information would you need to confirm the conditions for this test have been met? Okay, so it was a random sample, so that's good. 41 boys, 41 girls, so I'm expecting at least 410 boys and at least 410 girls at this school. That's the information we would need to know. We don't really know there. Okay, and then they're both at least 30, so we don't have to prove the normal condition with the data, so we're okay with that. But we need to know approximately, is it a really large school, big enough for that to be less than 10%? Okay, construct and interpret that. So in this case, we're talking about mu of B and mu of girls, boys and girls. And so you talk those in context, the true mean, in this case, height of the boys and true mean height of the girls are those two variables. You write down the confidence level, which is 95%. Then you go to just check your conditions next. So random sample. So random sample, go and just write it. Random sample, check. Less than 10% condition. So we think that 41 is less than 10% of the population at the school. And 41 is greater than or equal to 30 in both cases. That you might want to put in both cases for all of those, really, because that's really what we're saying. So it passes the condition. So then you might consider doing this in your calculator. So menu 6, 5 is interval. Oops, 6 is interval. And so this is going to be a 2 sample t interval. We're not going to use data, we're going to use stats here. So X bar is 54.31, 1.62, 41, 53.63, 1.85, and 41. 95% sounds about right, and no pooling. Okay, so we have all the data there. That's actually really helpful. So now we can plug into our formula, I believe. So it's going to be 54.31 minus 53.63. That's like our first thing, plus or minus. You're going to want to figure out the t critical value. So the command would be inverse t, because 95 would be 0.975. It looks like the degrees of freedom is 40. Definitely write that down somewhere. Degrees of freedom equals 40. So we get a t value when you type that in your calculator. You get, I think, 2.021 times the square root of 1.62 squared. It's hard to read that, but over 41 plus 1.85 squared over 41. Okay, and then we just simplify that using the data from our calculator at that point. So X bar, the difference is 0.68. Plus or minus margin of error is 0.764. So we get a lower bound of negative 0.08, comma 1.44 or something like that. So this one just says interpret, I think. So we are 95% confident that the interval from negative 0.08 to 1.44 contains the true mean. Then say that in context. Does sleep impair intellectual performance? Researchers examined this commonly held belief, comparing the performance of different subjects in the morning to normal light sleep, and extended sleep. I don't think this is a problem for most of us. The order of these treatments was determined randomly. That's good. In the morning, they were given a number of tests to see how quickly they think. The lower the score, the more alert the subject. Okay, so we really want to get the differences here. So the differences in that one is 0, 0, 14 minus 17 is -3, +2, -9, -5, -6, -12, I believe, -7, and 8. Okay, so I would consider just typing those data into your calculator. I'm going to go to Doc, Insert, Page, Problem. So now when I put list a spreadsheet, I can call this one diff and not have to worry about it's not going to be there already. So 0, 0, 0, -3, 2, -9, -5, -6, 6, -12, -7, and 8. Okay, type in all the data, go to the calculator page. Let's go ahead and do the paired t-test. So it's menu 66. It's just a t-interval. We'll go with data, choose as a diff. I'm pretty sure it's 95%. Ooh, let's do 90. Okay. Standard deviation, by the way, is 5.86. Calculate the mean difference. The mean difference was x bar of the difference was -3.2. Let's see, alertness score. So I guess you want a higher score. So ooh, it's negative, which means extended sleep would be a higher score, right? So negative numbers indicate extended sleep is better. So maybe it does help us, I guess. But we're going to see, do the interval and see. We have to interpret the standard deviation. So in this one, varies by 5.86. So the difference of extended sleep minus normal sleep and alertness scores typically varies by about 5.86 from the mean of -3.2. Okay, so then you talk about what is the mean of the difference. So you're going to define mean of the difference is the true mean difference between the alertness scores of normal sleep versus extended sleep, normal minus extended sleep. Confidence level, make sure to mention it. It's 95%, 90% here. We're going to do a one sample t interval. Check the conditions. Random, I'm looking for it up here. Let's see the word random. Oh, the order was determined randomly. The order was determined randomly. So they assigned the treatments randomly. So this, it's interesting. I don't think we have to check the less than 10% condition because it's an experiment. They volunteered for this. It's not like they were randomly chosen. But there was random assignment, which is good. So I would say that the condition there is random assignment, right? They were assigned randomly to the different treatments. Okay. 10% is not needed. Large sample, if you draw the dot plot, so then you would draw a dot plot of this guy. It roughly had this look to it, and you're going to label the axis and do that. But It's the differences of extended sleep minus that kind of sleep. And it looked roughly symmetric, or at least not strongly skewed. So that looked okay. So ready to start. I would do this in your calculator. Do we already do that? We did. Okay, so we have a lower bound and an upper bound. So I like to plug in just so you see it. And so I'm just going to show you the answer here. There it is. So this is finishing off that work right there. Just writing that down. Once you know your interval, we are 90% confident the interval from -0.2 to 6.6 captures the true mean difference of extended sleep minus normal sleep and alertness scores. I think I did mine in a different order. I did normal sleep minus extended sleep. So that's okay. As long as you say which one you did, that's perfectly fine. Okay, that's your screencast for today.